Hello everyone. Today we're going to learn one of the most powerful data structures used in graphs, networks, and real-world systems. It's called Union Find, and this structure answers very simple but extremely important questions. Are these two elements connected? How many independent groups exist? How big is each group? So in this for this data structure, we're going to use the DAT technique and recursive function, just so you know. And before we jump into the real example, there is the two important rules. First things first, in union find, if two elements have the same boss, ancestor, leader, root, parent, whatever it is, it means they belong to the same group. And important number two, when we union two elements, the ancestor of the right parameter always become a child of the ancestor of the left parameter. So this is like an unofficial rule, but I'm gonna tell you later what this means. Well, like I said before, we're gonna use the recursive function and DAT to implement the union find data structure. And so we can mark the leaders in this array. So union 3 to 2, which means that um, the leader of node 2 is 3, and we can draw the structure like this. So the leader of node 2 is 3. There we go. And when it comes to union 2 to 1, which means that um, the leader of node 1 is 2. So it goes like this. And so we can draw one more node over here, which means that the leader of node 1 is 2. So this is the entire structure of this code. But when it comes to node 3, it is filled with 0, which means that this is the final leader. And so, yeah, this is our base condition when it comes to recursive function. Well, if you take a look at this structure over here, node 1 and node 2 are the each different group, but once we execute this code over here, union 1 to 2, which means that um, the leader of node 2 becomes node 1. And we draw the structure like this. And what if we execute this code, union 3 to 9? Then in the union find data structure, calling union 3 to 9 does not directly connect it to 3 and 9 like this. Instead, it finds the root of 3, which is 5 over here, and the root of 9 would be 8 in this case, and then links those roots together, forming a single group like this. So now I'm going to show you how to implement the union find data structure using this example over here. So just write down the basic code first. Well, we need the leader array, and there is the find function first. So we're gonna use the recursive function if leader n, which is 0, I'm gonna return n, which is our final leader. Otherwise, we're gonna call the find function again. And then I'm gonna make the union. We're gonna find the root A using find function. Well, if root A and root B is same, we're gonna return it because they have the same leader, same group, I mean. Otherwise, we need to union two different groups into single group. There we go. So well, we can union 5 to 1, 5 to 1, and 5 to 3, and 8 to 9. There we go. And so we can figure out whether those groups are in the same, those members are in the same group or not. So you can throw in the random numbers. If the leader are the same, it will be a same group. Otherwise, it's going to be a different group. Well, this says different group, but if I change the number like this, same group, it says the same group as well. So there we go. Well, in the union find data structure, path compression in the find operation works by updating each node's parents to the final leader as the recursion unwinds, which is 5 in this case. Specifically, the find function returns the final leader, and while returning from the recursive calls, it assigns this leader to every node along the path. So it's gonna be reconnected to here, here, and it goes like this. And so as a result, all visited nodes are directly connected to the root, which is 5. Although the first find operation may still be slow, but subsequent find calls become much faster, often close to O1 time complexity, because the tree becomes almost flat after path compression. So in the Visual Studio, this one code makes the huge difference. So it becomes much faster. This is called path compression. There we go. Well, now let's move on to our next example. Imagine an online study platform. Each number represents a student ID starting from 1. And at the beginning, every student is in their own study room working on the different projects. When two students decide to work on the same project, their study rooms are merged into one. And this merging process is what we call a union operation. So over time, multiple merge requests happens. So this is the number of requests. So there is 4 merging requests in this test case. Well, in this problem, we don't really need to worry about this number. This is just the number of the request and query. And our goal is to efficiently answer 2 important questions. So first, how many independent study rooms currently exist? So this is result of merging, so it's going to be 3. And second, how many students are in the same study room as a specific student? So we simply take the student IDs from the input which is 1, 4, 6, and figure out which group each student belongs to and output the size of that group. So it's gonna be 3, 2, 2 based on this input data. For the question number 1, we can get the total nodes, the number of the nodes using the DAT, and subtract with the number of successful union operations. Then we can figure out the number of groups. And for the second question, how many students are in the same study room? So um, yeah, to calculate the size of the group, initially every element forms an independent group, so we initialize each size value to 1. And during a union operation, we can merge using the size array with this. So this is how we merge the groups and manage the number of the members in each group. And so I'm going to copy this test data. Well, first things first, we need to add the new text file. I'll name it cin.txt for our input data. So I'm going to save it. Well, this is our previous code, so I'm going to erase the main function. But other than that, it is still reusable, so I'm going to leave it. First things first, we need the size array and DAT to get the total nodes, the number of total nodes. And we need the successful union to get the number of the groups. And well, if the union was successful, I'm going to increment this value, and I'm gonna merge the size with root A with size root B, and I'm gonna make size root B to 0. And let's move on to main function. In this case, we need to open the cin.txt file with read mode, and this is how we access the text file. And so we need the two student ID to merge each other, and if DAT A is 0, I'm gonna mark it as visited, and I'm gonna set 1 with the size array, and I'm gonna increment the total nodes value. And I'm gonna do the same thing with the node student B. There we go. And so yeah, so this is all about the union part. So we need to do the union operation with A and B. So yeah, we can get the group count by subtracting total nodes with successful unions. So this is how we get question 1. And there should be a question number 2. Need the query. Well, we need the student ID, and student ID and the group size. We're gonna figure out the group size by accessing the size array with finding the final leader in each group. So this is all about the coding part, I guess. So if I execute this file, yeah, let's compare it with this picture. So there is 3 groups, and in the group in student 1, the group size is 3, and the group in student 4 has the group of 2, and the group of student 6, they have the group size 2, as you probably can tell. So this is how the union find data structure works. Well, this is our last example for today. So how do we detect a cycle with union find data structure? And so based on this code, I'm going to connect each node 1 and 2, 2 and 3. I just skipped this part for the further explanation. So if 2 nodes have the same leader, which is between 3 and 1, which means there is already a pass between them, which is this pass. But trying to connect them again as a new edge to an existing pass, which forms a closed loop over here. That closed loop is exactly what we call a cycle. And so this is all about the explanation. Well, this is our first code in this video, and we're gonna reuse this part. First things first, I'm gonna change this input data to 1, 2, 2, 3, 3, 1. This part is a cycle. 4, 5. There we go. I'm gonna save it. And we need to access our input file. Read mode with we're gonna input node A and B, and if we detect the same leader, it's gonna be a cycle. And we're gonna end this main function right away. Otherwise, I'm gonna union A and B. And if we survive at this point, it's gonna be no cycle. There we go. Yeah, it's a cycle situation, which is this part. And I'm gonna change this number to 6, 7, which is no cycle situation. No cycle. There we go. So this is all about today's video, and I hope you'll find it very useful through this video. Thanks for watching. See you on my next video. Bye guys.